Okay, so today's video, we're going to be doing the Fenske and Underwood equations. I think I mentioned this at the end of the Ponchon-Savarit, but yeah, we'll be deriving those equations. So Fenske, seen in our problem statement here, we have the minimum number of stages, and then for the Underwood equation, the minimum reflux. So we'll go ahead with those derivations of, based on our mass balance and then a component mole balance. Usually we do both the light key and the heavy key for both these equations, allowing us to obtain a ratio with our constant relative volatility after we substitute our, I think it was the partition coefficient or partition constant. I think that's the name, the big K, essentially the vapor mole fraction over our liquid mole fraction, that equilibrium ratio. So once we derive both of those, actually just in Python, right after that, we'll be finding our minimum reflux ratio. We're given some constants and known values here, and we'll plug that into our Python and just solve for that reflux ratio, the minimum reflux ratio. I think I'll also do I'll graph the function so you can visualize the roots like we did in class if you were in class. And then, yeah, I mean, let's just jump straight into it. So with our Fenske equation, we have, we're determining the minimum number of stages. Can't hear my music, sorry. So yeah, Fenske equation. I think that's how you spell it, right? Yep. Okay. Equation. So remember, we have our line, our binary XY diagram. We have our 45-degree line, and then our equilibrium curve. Remember, this is for Y's and X. Our mole fraction corresponding to each other, so they're in pairs. And remember our operating line, specifically for the rectifying line, it was R over R plus 1. And now since we're determining the minimum number of stages, we want this operating line instead of how it usually looks, something like, I don't know, like this maybe. Or I'm sorry, it should touch the line here. Instead of something like that, to have a minimum number of stages, you'll notice we break off at a certain point around here. So for a minimum number of stages, we want our line to actually be corresponding on that 45-degree line. So I'll erase that, but know that our operating line, that mass balance, we did for the passing streams of each stream from each stage, or well, those passing streams, I should say. That operating line, that mass balance, lies on the 45-degree line. So all of those passing streams have the same molar fraction. So with our slope of line, R of R plus 1, to get that slope of 1, our reflux has to become essentially approaching infinity. So as R gets very big, this slope of the line essentially approaches, say like approaches 1. So I don't know if this is technically correct, so maybe something like the limit of R approaching infinity. But, you know, infinity over infinity doesn't really, I mean, we could say it equals 1, but technically it's infinity is a concept, so let's not go there. But essentially, that slope is becoming 1. So our 45-degree line is now our operating line. So that being said, we have our stages that we always do. So we draw from our condenser, which we always know as our vapor mole fraction coming up is equal to the liquid mole fraction coming down. So let's actually just draw this out. So I'll do 3 stages. And this will help us determine, well, we know the number of stages, but just to kind of visualize, we have passing streams. Maybe this is n, but we know n is 0 usually. Well, it is for our condenser. So let's draw this out. So there's actually, I'm drawing these streams out, but we actually have infinite reflux, or a very big reflux. And remember, our reflux ratio is our reflux over our distillate, what we're taking out. So if this becomes very big, you'd imagine that the distillate is very small. And essentially, approaching that infinite reflux, we're taking out almost no distillate. And it's essentially a full, how should I say? Well, I wouldn't say the reflux is increasing, more like the distillate is decreasing, such that the reflux becomes very, very big. So yeah. That being the case, oh yeah, I was going to X out these streams. So now we're not taking out a distillate or bottoms. And actually, we're not even putting in a feed. So we'll do this based on the n stage, even though this is technically 0. I'll just write it in terms of n. But we know our mass balance can always be applied. It might be better just put this as n. So this middle stage here. So let's do our mole balance here. Where do I want to do this? Let's do it here. Yeah, sure. So remember, we usually have our balance at the condenser being something like our vapor going in. Okay, still recording. Our vapor going in at the stage below is equal to our current stage of the liquid flow rate plus our distillate, but we don't have a distillate, so we just say that's 0. And then now we do our balance for our more volatile component, usually our light key in this case. Well, it doesn't have to be the more volatile, but we'll say it's our light key. If you remember, we talked about the light key and the heavy key in the previous video, I believe, on the degrees of freedom analysis. So go check that out if you don't know what I'm talking about. But yeah, since we know these streams are equal, remember these streams correspond to, well, I guess it'd be from here. So this is n plus 1. So this is the vapor going up from the stage below, and this is the liquid coming down at the current stage. So that being said, we do our mass balance, our component mole balance for our light key, which we denote with I. So we have Yi of our light key, our vapor mole fraction of the light key times, or at the stage below, times our vapor flow rate is equal to our liquid mole fraction at that current stage n times our liquid flow rate. And now, let's see, am I doing this correct? Yeah. Okay, so we know that the vapor and liquid mole flow rates are equal to each other, so these essentially cancel out, and now we're left with just our molar fractions. So I'll write this out. And now what we can do from here is actually we apply our partition coefficient, the K. So remember that K was essentially that ratio of vapor to liquid mole fractions. So I'll write for Ki, component I, which is our light key again. That's our vapor mole fraction, Yi over Xi. And remember, these are in equilibrium. So these stages actually have to be the same. So this, it doesn't help I drew it in the same color, but this expression refers to, make it white, refers to equilibrium stages. Did I do that correctly? I think so. I don't know, I'm confusing myself a little bit. Yeah, let's just write this out, see where it goes. Honestly, if we make a mistake, oh well, we'll fix it. So I believe we will substitute our liquid mole fraction so we can set our liquid mole fractions, and what you'll see is that our condenser all the way to our, if we specify our liquid mole fractions for our light key and heavy key, and J is what we'll use for our heavy key. If we specify those at the condenser and specify those at our boiler, essentially our last stage, and then we know our constant relative volatility, we'll be able to tell how many stages n we need to go in between to reach the condenser to the boiler. So let's that would be n plus 1. Am I writing this correctly? Okay. So it would be Ki at x. Oh. Yeah, I don't know if, okay, well, it should be Ki, so Yi, if we substitute it over, it would be so K, vapor mole fraction Yi at the current stage is equal to the partition coefficient Ki times Xi. So those actually match up, but in our derivation, I believe it was n plus 1, corresponding to the liquid coming down. Oh, that is correct, yeah, because that's interesting. Okay, well, we'll keep going like this. And then bring that down, we have xin. And then what this allows us to do, so I think these are actually at, instead of at equilibrium, these are at passing streams. So that's the only way this would make sense if we substituted n+1 and we got n+1. So these are at, I mean, if we look at, let's say this is n+1 instead, since the bottom is the boiler here. So if this is n+1 instead, we would have, and this is n, this would be, oops, is that the right color? This would be vapor of n plus n. This is liquid of n. And we just substituted out the y of this stage with the x coming down. So yeah, I'm sorry. Yeah, that is correct. It is equilibrium. I think I was confusing myself since I was looking at the boiler and I was like, there's no stream coming from the boiler. And normally you don't do this for the boiler. So anyways, so that's correct. This is referring to equilibrium. I didn't misspeak. Sorry about that. So now, yeah, we have this expression, and normally we also do this for the, again, I mentioned the, we'll use J for our heavy key. So we do this mass balance again for our heavy key. So I'll just, it's honestly simplifies to the same thing. So except we're doing this for component J, our heavy key. So that's xj at stage below is equal to the current stage with our heavy key. And remember, now our next key step here is our relative volatility. And usually this is done in terms of our heavy key. And what I'm saying is that reference point underneath this denominator is our reference point. And this will also be the case for the Underwood equation. Usually this is the case. I imagine there are other scenarios where it's not, but for our case here, we'll use the heavy key as our reference. So that's Ki over Kj. So remember, our constant relative volatility is the ratio of these K terms. Or honestly, I should look this up later, so I'm not misspeaking. So K terms, I don't know. I'm blanking on the word right now. So yeah, if we divide across, just like that, so that's our new expression. We bring that down, we'll evaluate Ki over Kj as our constant relative volatility between the light key with respect to the heavy key. So that's alpha ij. And then now we have our liquid mole fractions of the light key and the heavy key at the stage below, relating now to our liquid mole fractions of our heavy key and our light key and heavy key at the stage above, or the current stage. Now there's a way we relate between stages, and you can imagine as we go from stage to stage, as we start from our condenser all the way down, we'll be building up on these alpha terms. So let's write this explicitly with our three stages here. So with our three stages, what do we have? So we're starting at 0, so n equals 0 at the condenser again. So at 0, or I'm sorry, I should label this is our light key and our heavy key, and then we're at 0. And remember, we relate n to n plus 1. So then n plus 1 would be stage 1, obviously, because we're going down. So we have, again, our light key and heavy key at the stage below, so 1. Then times, now we have this alpha term, our constant relative volatility. So that's 1. We have to get to, well, honestly, just 2. So we just do it one more time here. We'll repeat that again with our light key, heavy key at the current stage, 1. Relate that to the stage below, light key and heavy key. So add 1 to our n, which is now 2. 1 plus 1 is 2. Make sure I'm not messing this up. Now we have another alpha ij. And honestly, we're done. Since we only have these, well, technically labeled 2 stages, 3 stages overall. Am I doing that right? I'm sorry, it's 2 stages in addition to our condenser. So since you'd only have 1 stage, no tau ij, since you're not going to another stage. So for an additional 2 stages, we have tau ij, 2 tau ij's. So if you combine these expressions together, well, what do we have? So we have our initial starting at the condenser, and light key, and then this is our heavy key at the condenser. And well, this is equal to the stage below 1, and I'll refrain from writing that now since we'll have to rewrite it. So it'll be that ratio between our light key and heavy key from the stage below, but we have this alpha ij term, so I'll have alpha ij. And now I waited to rewrite this since this term again is being substituted with another expression from the stage below it. So now we rewrite that term as this, which is just 2 stages below. So we have another alpha ij term, and we have our light key and heavy key for the stage below. So now this is 2 stages. So for an additional 2 stages, we have 2 constant relative volatilities. So you can imagine as this goes on and on, you would have, well, this is essentially ij squared, and this is also at 2. So this 2 and 2 naturally are related to each other. They keep increasing by 1 incrementally with each stage. So now we just replace them with n. Since for every n, they will correspond for any nth stage, light key and heavy key down here. And also, always, this relates to our top stage at our condenser, light key, heavy key. So now this is our expression. So n for any n stages, well, we're solving for that minimum number of stages here. And of course, this is assuming at infinite reflux, where the slope of our operating line, those passing streams are equal to each other, such that the operating line lies on the, I just noticed I'm off-centered. The operating line lies on the 45-degree line, as I showed before. So since we're solving for n, all we have to do is divide this baby over. So that is light key and heavy key ratio of our liquid mole fractions at the initial step. I don't know why I drew it so big. And then that's over our final stage. Again, a ratio between light key and heavy key liquid mole fractions equal to alpha ij, the nth power. But you notice if I take a log of this, so I'll just do it to be explicit, I'm going to also call this a, so I don't have to keep rewriting. But remember, that's a ratio. Those are the ratios between our condenser and our, well, the last stage, those liquid mole fractions of the light key and heavy key. So I'll just call that a, and I'll take the log of a is equal to n log of ij. Remember, this is equivalent to log ijn, and you take the exponent out as a coefficient, n. And then now you have n stages. Your minimum number of stages is equal to log a over log tau ij. Or not tau ij, alpha ij. There you go. Yeah. I guess I can also rewrite this for the sake of clarity. Remember that a was that, can I copy paste this, honestly? There we go. Because I'm lazy. We're going to be derivating for a while. Is that even a word? Deriving? We're going to be deriving for a while, so pardon my laziness. So log alpha ij. And that's our expression for the minimum number of stages. So that's a little messy, but we got there. So we won't be coding that out, but there you go. That's what the Fenske equation is. Again, I drew it on a binary XY diagram, but you can imagine for multi-component where you can't graph this out, it becomes a lot more useful and easier to use, or more helpful to use, in which case you can't visually see where that slope goes to 1, and you draw those stages by hand. For multi-component, you would use this, essentially. Okay, so for Underwood, we have minimum reflux. So let's make a divider here. Minimum reflux, so Underwood, let's draw our line again, our binary XY diagram once more, just to visualize. A 45-degree line, our equilibrium curve, and now for Underwood, we have a minimum reflux. So imagine the pinch point. I think we saw this earlier when we did distillation columns a while back. Maybe it was our first or second, but these pinch points, it's this idea of a minimum reflux, where our operating line has to hit a certain point before there is such thing as a pinch point where our slope essentially approaches, instead of 1 this time, did I write 1? Okay, yeah. Where instead of approaching 1, it approaches 0, a horizontal slope. So I'm trying to draw this in a way that makes sense. Maybe something like that. So you would start on your line, so that's actually really on point. But anyway, draw your stages as usual across the, well, you touch your 45-degree line at the start, since we know our condenser, the vapor going in is equal to the liquid and distillate coming out. Those are in equilibrium, and they are also the same. They're equal in mole fraction. Anyways, going down, and then eventually you hit a certain point where you can no longer cross. So there's this pinch point right there. And essentially what that means, as you keep on approaching, no matter how many stages you do, you keep going maybe until infinity stages, what's happening is that your vapor mole fractions as you're going down, since remember, as we draw the number of stages you're using, let me draw this out. So as we draw those stages, what we're doing is we have the mass balance as we touch our operating line. And with that mass balance, we go to, since we know one of the streams here, we know the equilibrium coming down from the stage below. So we use one of the streams here that we got from equilibrium. So one of these streams here from equilibrium, or I'm sorry, mass balance, since they're passing streams. And then we use one of those streams to get the equilibrium, since this stage is in equilibrium. Okay. So no matter what we're saying is that at that pinch point, no matter how many stages we draw, what ends up happening is that we can't get, well, we can get a different line, but it's not significant here. We can't, this stream is not as significantly different from this one. So what I'm saying is that this vapor mole fraction, if this is Yn, is nearly identical to the liquid mole fraction, I should say. Xn plus 1. Or I'm sorry, that's not correct, but Yn plus 1. Because once we get this liquid mole fraction, sorry, I think I misspoke again. So once we get this liquid mole fraction, this equilibrium here is what's not different from here. And of course, the same thing would be the case for this liquid stream. So again, to reiterate, when we're drawing those stages, we're using that mass balance of our operating line to get one of these passing streams. We use those passing streams to obtain a equilibrium from the streams below, and so on and so forth as we get these pair of streams. And what's happening is that as we obtain a stream below, this stream below corresponds to an equilibrium that is not different from the stage above. So essentially, this vapor mole fraction is not different from the vapor mole fraction below. And you'd imagine the same thing is the case for the liquid stream. Liquid mole fraction. And this is at n equals into infinity. So they're nearly alike. And we'll be using that in our determination of this minimum reflux point. Again, remember our reflux is equal to our reflux over our distillate. So with a minimum reflux, we need to obtain values of liquid flow rates and distillate flow rates that correspond to that minimum reflux. And we actually obtain this through substitutions. We can obtain a vapor flow rate, and I think we're given a distillate. Or actually, we can get that distillate by using our recovery, which is specified in our problem statement. But remember, I should write it like this. So we use our balance. Our vapor is equal to our liquid plus D. So we substitute our liquid as the liquid, well, that's our reflux is equal to, did I do that correctly? Yeah, so I'm sorry. It should be, so we substitute our liquid here is equivalent to RD, and we substitute it here, I'm sorry. And then we do reflux times distillate plus our distillate, and then we obtain a means to acquire our reflux ratio here, as long as these two components correspond to, well, usually just our vapor flow rate corresponds to, I don't know, a scenario of that pinch point. And then our distillate is obtained through our problem statement of the recovery. And then we can obtain this R. So it would be, let's see, V over D minus, I don't know why I drew R, U divided by D, divide that over, and then minus 1. So we're trying to obtain this reflux ratio from this expression. So we need vapor flows and we need a distillate flow. So these are total flows, I should say. Yeah, so let's just start our derivation here. So I think that's the point I wanted to make. You know what, I'll also go over this. So we also, remember, it's not just our rectifying, but we also had our stripping, which had a slope of r plus 1 over r. And if you imagine, as we do infinite stages, I'm sorry, so we had r over r plus 1, that approach 0, a slope of 0 as our reflux approaches 0. And remember, our reflux approaches 0 because we are making our distillate very big. Yes. So if our distillate is very big, then our reflux ratio must almost as if we keep increasing our distillate, then our reflux ratio approaches 0, which allows our operating line, well, I should say, is a result of our operating line having a slope of 0. So anyways, what I was trying to say, stripping line. So now the slope is flipped, but if r approaches 0, then we have an undefined divide by 0. So it essentially becomes a vertical line here. And I use white there. So maybe something like that maybe. And you'd imagine we also start from our mass balance. Wow, that was horrible. Start from our mass balance. And we draw the corresponding curves. Did I do that correctly? And then you approach another pinch point. So you notice that these pinch points are the same. And no, that's not just my horrendous artistic ability. It's also because the pinch points don't have to be the same. Imagine the slopes of the lines obviously change. That's how we drew our first distillation column of our stripping operating lines. Remember, we derived those. But again, you'll see that you could have multiple pinch points for not just you can see now with our binary component here, but in multi-component, you can have multiple pinch points. So I mentioned that because we'll also be doing a balance for the boiler from the stripping section, essentially. So let's start our balance. I mean, I can just draw the condenser here just very quickly. Vapor going in. So we have vapor from the stage below, liquid coming down, distillate. We have our usual balance. Done this a million times. Plus D. And we do our component balance for the the light key again. So that's our I at the stage below. Remember, we match up molar fractions. So this vapor flow rates and liquid mole fraction with liquid flow rate plus our, and then we have our distillate. So remember, this is still our light key at the distillate times our distillate. So I'll try to be specific there, since we'll also have our heavy key again. To obtain that constant relative volatility, we'll have to get that K1 or Ki. So the first thing we do is, well, we're at infinity, so n equals infinity. So I'll write that again. Essentially, the vapor flow rates are the same. So I mean, I'll take out the stages. We have infinity for our yi. I'll just write v, and then since it's understood from the stage below, xi at infinity and L, and then distillate does not change since that's part of our balance. So the key step here, again, once more, is this K term. I keep calling it partition coefficient, but I'm not 100% on that. So again, it was Ki is equal to the equilibriums. And remember, since these are now at infinity, they correspond to one another since they're equal. They're equal equilibriums, if that makes sense. Since the streams from the stage, the passing streams between each stage are now equivalent since we're approaching infinity, And we have our expression we did before. That almost confused me. So we do the substitution for our x, our liquid mole fraction. So we have y at infinity times our vapor flow rate, and then x is equivalent to yi, light key, vapor mole fraction at infinity over our ki, times liquid flow rate, and then our distillate. And this is actually distillate recovery. So that'll be important later. That being the case, we can factor out this yi here. And then we have, if we move this over to the left-hand side, we have v minus, and that's L over ki. And this equals our distillate, which is positive. I think in the bottoms for our stripping, this is actually negative, since our balance is different. But anyways, now we isolate our yi. So I know these steps, these algebraic steps kind of seem trivial, but they help us do, I don't know if I explained this before, but this is, even though it might seem complicated, this is actually a shorthand version, or a shortcut version, I think is what they call it, for a distillation column to determine the minimum reflux. With Underwood, it's a lot more complicated, especially with multi-component, and he proves a very significant step that allows us to find that minimum reflux, which comes a bit later after this. So bear with me for now. Since we have this all equal to our vapor mole fractions at infinity, remember that vapor mole fractions sum up to 1, so we apply the sum rule there. So it's sum of our infinity vapor mole fractions. You could say from I equals 1 to big I for however many number components we had, and for infinite stages. So that's what the sigma represents, so I'll refrain from writing that from now on. Hopefully that makes sense. And then that's equal to 1, and then we have our sum for the right-hand side, and I'll just write that down. Copy that down. Vapor minus liquid flow rate over Ki. So here's where the algebra really does seem very trivial, but yeah, keep on bearing with me. So first I'll divide by V on the right-hand side here. So that leaves us with our liquid mole fraction, essentially times the distillate, which is essentially our recovery, but we divide by vapor. Fraction, remember when we divide a fraction, all the terms in a fraction by the same thing, it's still equivalent. It's like dividing by 1. Remember, that's how we used to rearrange our terms. So v over v is 1, and then this second term on the bottom, this denominator, also divide by v. Now we multiply by v on both sides, so we have v, and then only the vapor on the numerator gets canceled out, so it's still back, almost back to normal. Except we have this vapor term, and denominator, well, both of the terms in the denominator have been modified a little bit. After that, we multiply by Ki on just the right-hand side. So recovery here, liquid mole fraction of the light key times our distillate, which is our recovery. Both of those terms multiplied together is our recovery. So this is multiplied by Ki, partition coefficient, the vapor mole fraction and liquid mole fraction at equilibrium, the ratio between those two. And I said multiply by Ki here. So 1 minus 1 times that is Ki, and we get rid of it for our second term here. Now this is where we add our heavy key. So remember, I is light key, J is heavy key. So this is that split. If you have multiple components, it's a split between two components. The lighter component is obviously lighter key, heavy key. Light key is more significant in the distillates, heavy key is more significant in the bottoms. So yeah, now we divide by Kj on both sides, which remember, that allows us to obtain our constant relative volatility, where we have a reference of Kj. Yep. And now this is equal to, this is again only for the right hand side. So we have our distillate times that. So divide by Kj is now alpha. So this is alpha, right? And then alpha once more if we divide Ki. And then now we have a term L over V times, or well, I guess divided by Kj. And usually we write this term as phi. I'll rewrite that just one more time so it looks a little better. So maybe something like this. Recovery for distillate times our constant relative volatility. Again, alpha, and then phi, where phi is equal to that liquid over vapor times kj. Okay, so this is our final expression for that vapor. And honestly, from here, we could just do our problem statement for minimum reflux. This is for rectifying, but I'll also show it for the stripping section, since you could also do this Python method for the stripping section as well. Since if you have either the vapor or V bar, the vapor flow rate in the stripping section, if you have either of those in either section, either flow rate, then you'll be able to calculate the other. Since remember that relationship is just vapor, it's another mass balance. So the vapor going up is equal to the vapor from the section, well, the vapor flow rate from the stripping section. So this is rectifying and this is stripping. And then that's addition to our feed, since the feed comes up and joins the V bar as it goes up to the rectifying. So that's our feed. I don't know, I switched colors. That's our feed times our vapor component. Remember, quality is our liquid fraction, Q. So if we had Q equals 1, that's a fully liquid feed going in. And I don't think it mentioned it. It mentions it in the problem, but we'll be doing Q is equal to 1 to simplify things. So that is our expression for the distillate, for the vapor mole fraction, or vapor flow rate corresponding to a minimum reflux. And we'll be solving for this term to obtain this vapor flow rate. And this term, phi, will coincide. You'll see that this expression for the stripping section is almost nearly identical, but we'll have different terms here for this second term in the denominator. And I don't know, it's kind of a waste to explain it now since you won't understand what I'm saying. So I'll go ahead and just derive that next part here. So we'll do for the boiler, so the stripping section, I draw it really quick. And we're at n, so this is Vn, this is Ln. Well, we can make this n plus 1, and this will be a stage above, that's n, since I don't like writing n minus 1. This is Ln, and then this is our bottoms. So we have our mass balance liquid at the current stage is equal to the vapor coming up plus the bottoms, component mole balance, xn. Well, and also this is for the light key. So correspond our mole fractions here. +1 and +1. And then this is our bottoms light key, which is also our recovery. That's moles per second. What else? Yeah, so we'll isolate our vapor again. And remember, this should be, I almost forgot. They should have a bar since they're in the stripping. I might forget to do that. So I also might, oh, whatever. Okay, so I'll move vapor to the other side. Rewrite everything here. +1. Liquid mole fraction. I messed up the order, but it's okay. And liquid mole flow rate. Just copying everything down. And then we apply, like we did before, n equals infinity. So now I write these vapor flow rates as, say, well, they're understood to be, well, vapor coming up, liquid coming down. So passing streams, essentially. And this is y infinity, our light key, liquid, multiplied by liquid mole fraction at infinity. And then copy down the bottoms, recovery. And we apply our partition coefficient, ki, once more. These correspond to, that's not true, yi, vapor mole fraction, and xi. And these are in equilibrium. And remember what we said, that they're equal. between stages. They're not increasing or decreasing. They get stuck at that pinch point, which allows us to say, I'm going to put it in front. It's annoying me. So yi infinity, light key at infinite stages times vapor flow rate, the stripping, equal to, and xi moves over. It's, again, our vapor mole fraction at infinity divided by our partition coefficient times our liquid flow rate, and copy down our bottoms recovery, still there. Factor out, kind of see it follows the same exact steps here. So V bar, oh, I'm sorry, I messed it up here. So when I moved this vapor to the other side, why am I using red? When I moved this vapor to the other side, I had to move to this side, obviously. But I forgot to apply a negative sign. I was like, where did it go? So let's erase this, and this, and this. Wow, I did it a couple times. So vapor minus, did I even move it? I moved it down here on this third line, sorry. So when I do liquid minus bottoms, liquid minus bottoms, liquid minus bottoms. Good thing I caught that. Okay, so that's vapor, V bar, and then factor out L bar over Ki equal negative, then recovery of the bottoms. Again, moles per second, isolate yi, so we can apply our sum rule. I might just do that one step here. Sum equals 1. Do it a lot at the same time. We did it before, so we're good. We know what we're doing. V bar, L bar over Ki, making sure we're recording. My goodness. Okay, 40 minutes. So I believe what we did last time was divide by V. Copy our recovery down, divide by V. This is V bar. Sorry. Did I do that already? Okay, cool. And we have V bar is 1, divide by V bar Ki. Multiply by Ki, or I'm sorry, multiply by V on both sides. So we have V bar, some recovery is now just, well, it's recovery on the numerator. And that our denominator stays the same since we multiplied across, only across. L bar over V bar times Ki. Multiply by Ki. Hopefully this doesn't get boring. Multiply by Ki, and then L bar over V bar. And now divide by Kj, which is our, allows us to get, again, this is reference to the heavy key, this partition coefficient, heavy key of the, or partition coefficient of the heavy key, then Ki. So divide by Kj on the right-hand side only leaves us with some recovery times bottoms is, so we divide, and that's our constant relative volatility, alpha ij on the bottom since we divided more, and then we have this L bar over V bar and divided by Kj. And this is actually, in class, I believe we use omega. In our textbook, we use phi prime. So I'll go ahead and stick with omega, but this is our final expression. So hopefully, I think that went faster since I wasn't explaining all of them. So I'm just applying, just rewriting for omega, just because I can, so it looks cleaner. And omega, that is a horrible omega, something like that. So that's our box equation. Nice. So we actually won't be using this, but again, did I explain this already with the Underwood? Yeah, I did this already with the pinch point. So this would be a pinch point from the, oh my, what happened there? This would be the pinch point of our stripping section. And again, it doesn't necessarily have to be at the same pinch point at our rectifying. But what Underwood says, so let me copy down this one. Copy this down since we're not quite done yet. Almost done. Thankfully. So I just copied this down. This is our, what happened? Wow, he's the same colors. That's cool. Yeah, this is our rectifying vapor with a pinch point. This is our stripping vapor flow rate with a pinch point. Now to relate these two, so we actually get a minimum reflux ratio. what we're solving for, remember, were these two terms. Everything else here we should know, since we know our components going in, and this vapor actually gets canceled out when we subtract these two equations. So there's two things we have to do. We're subtracting these flow rates, so we get a pinch point that is relating both our rectifying and stripping lines together. So there's connecting those two sections together, which allows us to get, well, it's our minimum reflux ratio. And with that, we also have the key step I mentioned earlier with Underwood. Underwood says that this phi and this omega, which again was phi prime in our textbook, these two terms had a common solution, theta. So they actually converge to the same solution as a same pinch point. Well, it relates our pinch point. And you'll see that it depends on the number of components we have. If we have 4 components, there's 4 roots to this answer. And essentially what we'll have is, of those 4 roots, we'll have to choose the root that corresponds to our light key and heavy key. So kind of to visualize this, I don't know what the numbers we use in class, so maybe I'll do something quick, like I have A, B, C, D components. Let's draw these out. And then let's say B and C are our light key and heavy key. And this is our split right here. We have tau ij's, or not, I keep saying tau ij's. Alpha ij's, sorry, I'm just doing reactions. Alpha ij's, and we have our input feeds, our feed molar fraction. So I think in our problem, it's 0.25 for all, since it's 4 components, and it said it was equimolar. So 1 divided by 4, 1/4. And then these alpha ij's, these constant relative volatilities, these are all different, but they all are in respect to usually our heavy key, which is in this case C. So I mean, that's also what am I doing? It's not alpha, it's K. Kj. So this is corresponding to, in reference to our heavy key partition coefficient. I will look that up. I will make sure I'm saying the right thing. But anyways, those will all be different. I think in ours it's 3, 2, 1, and 0.5. So the reason this is 1, usually we use the reference again as this K value is, well, relating to the heavy key. So when you divide, well, it's essentially, we divide the Kj over Kj. For A, so this is for C, I don't know, alpha C, if that makes sense. For alpha A, I mean, it's not really alpha ij anymore, but anyway, so for the relative volatility of A, we would say it was Ka over Kj. So you're dividing all of these by in reference point. That's our reference point to the K value of our heavy key. So that's a little aside, but want to get that out of the way. So what we're literally doing with these equations is we substitute our recoveries. Well, we know, you know what, I'll just simplify the equation so I can write it out. So anyway, subtracting these two equations, rectifying minus stripping, we have V minus V bar. I'll write this all out. Summation, and then we subtract the rectifying from stripping, so we factor out Ij, constant relative volatility, and then we subtract our recoveries from the distillate, and then minus a negative. Remember, bottoms here is negative in the numerator, so minus a negative is a positive since we're subtracting the two equations. Minus a minus, and then this is recovery of our bottoms flow rate here. And then actually our denominators are the same because remember of this key expression that Underwood showed. And that's through some very, very extensive math or calculations that show that I won't be covering. I think we might get shown this in class later, but it's besides this point. So this is alpha ij minus theta. So now we have one expression. We can go a little further with this since we know, well, one, we've seen this before. This was, where did I write this? I wrote this somewhere really early on. It was about our feed being equal, relating our feed and our vapor flow rates. Did I not write this? Wow, I'm surprised. I thought I wrote this earlier. Oh, right here, yeah. So it's relating our vapor flow rates to feed. So if I go ahead and write that expression down, V minus V bar, and we had V was equal to what? V bar plus F1 minus Q. So it's V minus V bar. That's just F1 minus Q. So that's our feed, our vapor mole fraction. I guess our vapor mole flow rate, honestly, of the feed. So that's just F1 minus Q. And we can copy down the rest of this equation. But first, there's one more thing we could do. On this side, these are our recoveries of the distillate and bottom. So that's what we're taking out of the system. So remember, we have our feed going in, we got our distillation column. Kind of looks like a flash calculation, but we have our distillate and our bottoms here. So that's just a simple mass balance. Feed, distillate, bottoms. So those have to equal each other. So that means the molar fractions have to equal to each other. Something like that. I don't know why I drew 3 there. So Z, we write Z again. This is from way early on, but Z can correspond to liquid or vapor mole fractions. In this case, it'll be all liquid since Q is 1. I think I mentioned that earlier. So I think I'll just write XI, honestly. There we go. That's our balance. So essentially, what this means, I mean, it's understood that these are at bottoms, these are at distillates. So these correspond. That being the case, that means this parentheses, the sum of all our recoveries of our distillate and bottoms is just our fraction of our feed of each component. So Z is the fraction of each feed. Those, remember, those were all equimolar. I wrote them out here. This table. Okay. And all of that times our feed. So it's the flow rate of each component. So it's ZF. So if we write all of that down, we have a sum, copy down our constant relative volatilities and our denominator, and we have ZF. So notice now our feed gets canceled out as well. And remember I said Q is equal to 1. Since it's fully liquid, the quality of our feed is 100%. So if Q is 1, 1 minus 1 is 0. Now we have this final expression. I use yellow again. 0 is equal to the sum for however many components we had. Constant relative volatility, copy down denominator, minus this theta term, the Underwood found, times, now it's just our molar fractions of each component. So that should be the I there. Those correspond to, remember, we're doing a sum. So there's multiple values for these 3. And then we'll be using root scalar, since it's only one value here, to solve for this theta. So essentially in our Python, we're going to be, we have these values, plug them into here, use root solver. I think we don't, well, yeah, we'll use root solver in addition with that to solve for theta. So a visual representation, it's, sure, why not, I'll do it. So we have our taus, I keep saying tau, alphas, go to our alphas, and our z's go to our z's, just making sure you can see that. Okay. So zoomed out here, but let's start with component A. So 0 is equal to A, which is tau ij3, that's 0.25 over 3 minus theta, we don't know that. Adding, since it's an MP sum, so now it's 2, and then this kind of gets repetitive here. So 2 minus theta, 2 more components, so this is B, and this is C. 2 is 1, 0.25, then relative volatility is 1, last component D, and this is 0.5, constant relative volatility, equimolar, so they're all 0.25, and then 0.5 minus theta. So this is what we're doing in root solver. All right. I think we can finally go to our Python. So I'll keep this up if I need to reference. I'll definitely need to reference the vapor. So since we're doing this for the rectifying, I'll be referencing this to solve for a vapor. We'll need, what else do we need? I think I wrote this at the very start. We'll be needing this for our solving for our reflux, and then distillate is our recovery. So that'll be a total flow. We'll be summing up the recovery. So we get the distillate recovery. That, again, I mentioned that was the liquid mole fraction of any component, honestly, since we're going to sum it up. So liquid mole fraction times, why don't I just write this? I don't know why I'm saying it. So distillate is equal to a recovery. Remember, I called this term a recovery. So this will, I think I already have an array for this. Recovery. And then Is that it? Recovery, I'm sorry, then the feed, right? Did I say that right? Yeah, feed. So feed component. Bless me. And this is the molar flow rate of each component. So that'll give us if we sum all of this up, that'll be the total flow rate. So forgive me if I write too many variables, but it helps kind of keep track of what we're doing. I know the more efficient way is to just plug in the the variables, so we don't have to keep dividing, naming new variables for algebra, but just to kind of show it very explicitly, I'll rename variables like this. Hopefully that makes more sense once I do that. So, all right, just reaching an hour here. Got 30 minutes left for me before I have to go, but yeah, let's graph this. So I have my Python up. I do home collab. Let's run this. Okay, so imports are pretty simple this time, just numpy, root scalar from SciPy Optimize. We've used this before with I don't remember, when was this? I think it was not Ponchon Savret, but the one before that. It might have been, no, it wasn't Ponchon Savret. It was we were finding the intersection point of something. I can't remember, but we've used this in a previous video. Plotly as always to graph, and then I've gotten these from the problem statement. So we have equimolar. Remember I said 0.25. Honestly, let's just take a look at these. So then, I mean, those are kind of simple, but maybe Z's would make more sense. So again, if I multiply by 4, I think I did this in the last video. It's the first time I introduced it, but if we multiply this by 4, when we have it in this little list, it'll create, well, 4 things of it, if that makes sense. So it's very easy, so you don't have to type it all out. What are we doing? So at the start, I'm going to put my iPad aside here. We can actually solve this very easily, just going straight through with defining a function and then using root scalar on it. But first, I want to kind of show the function, since that's how you would find the root normally. Well, not normally, since we have root scalar, but it's kind of a visual way to see what root scalar is doing. I don't know, how do we want to start this? So at the end of the day, we are doing, let's see, let me split this. Right one, yep. Okay. And so I'm gonna go to our vapor somewhere here. There. Right there. Okay. So ultimately, at the end of the day, we're trying to find this vapor so we can relate it back to our reflux, minimum reflux somewhere right here. And then we have this distillate, so we can solve for that minimum reflux. So we have our, is that it? No, it's not here. We have our, no, what am I doing? I need this equation. I don't know why well, we'll need that later too. But we need to solve for this theta first. So we do that with root scalar. I'm sorry, I think I might have misspoken. So we know all these values actually already. The only problem here is this theta. So I'll be kind of creating a list of thetas to plot those out. Just kind of all the values in between our, well, it's just thetas in between our alphas, since those are where it has to converge. Remember, these 4 roots correspond to the 4 components, and the 4 components have 4 different alphas. So I'll create a kind of theta plot here. I think this is what he called it in class, our professor. Yeah, NP lin space. We created from, I don't know, 0.49, maybe 0.4, and we'll just go to maybe 3.1. So only going by a decimal place, or yeah, a tens place. And then we'll do 200 points. And notice that, well, you won't see it now, but later on, if we change these bounds and the number of points, our graph changes slightly, but the roots don't change. It's because the reasons why you'll see the, what are they called? The spikes, where it's divide by 0 error, since there'll be more points that approach these values. Remember, this is in the denominator, so if you plug in a denominator that's the same as the alpha for our components, this denominator becomes 0. So you'll see those discontinuities. That was the word. And before I go further, I think I want to look up K term. The partition coefficient. K values, partition. It is. Okay, so I wasn't making things up. It's called partition. Well, according to the AI, but that's enough for me. Yeah, partition coefficient. Well, now it says P. Whatever. Enough. Okay. So yeah, we'll be graphing those. You'll see the discontinuities and the graph will change. I can modify that to show the case. So let's go back just to full screen this. Let's go fig1 is equal to, well, I didn't even make our values yet. So we'll go like Underwood plot maybe, or I think he called it values. I'm just stealing Carlos's variable names. Underwood values. So wait, why did I do that? I need that equation. So can I move this a little bit? Oh, maybe like that. So for me, let's see. We have our alphas. So this will be a list. We'll be doing list comprehension. I think better just see this in action. And I already looked it up because I had to study it. Essentially, it's kind of a for loop. So you're creating data points and you store it in a list, and you do that for a condition. So you can do it for a range, you can do it for an inequality. In our case, we'll be doing it for a list, kind of looping a list of our theta values in theta plot. So if you see all our thetas in theta plot, quite a number, 200 of them. So we'll be plugging all of these into our equation. Here, right there. We'll be plugging those with our list comprehension. So we have, what is that? Alphas. So remember, alphas are an array. So these, since it's a sum, I do need a, well, no, I don't, I'm not trying to get one value. I'm trying to plot all of them. So we have our, all of our alphas. So there's only 4, and then we have 4 components. So again, 4 for our z's. Feed molar fraction going in. And yeah, that's all we need. And then we subtract our theta. So we have, I don't think I need parentheses at the start yet. So alphas times our z's divided by parentheses, since this is subtraction, alphas minus our thetas. And now this theta, we use our list comprehension. So it's 4 theta in, if I could spell, theta plot. So it's going through all those values you saw earlier when I displayed our theta for plotting purposes. We could take a look at that. It's going to be a very long list. Yep. And it will be about 200 points. Well, it should be to match up here. Can I, is there a shape I can do? I don't know. It should be 200, but I don't know how to view that. At least not off the top of my head. I could Google it, but let's just graph it. Since this is kind of this doesn't even need to be, well, this isn't even part of the problem statement, but anyway. Go as usual, add scatter. What is happening? X is equal to our theta plot, and Y is equal to our Underwood values. And let's make this dark so I don't have to be blinded. Template is equal to plotly dark. Same as usual, nothing new. And we can get rid of this. Oh, that's not correct. What happened? What did we do? Should be right. Alpha times, where's my equation? Alpha times z over alphas minus theta for theta in theta plot. Happened to you? Did I choose the right bounds? 0.4 to 3.1. Alphas times z's. Forgetting something. It'll be so obvious when I find it. All right, I'll pause here. I can't find it immediately. I don't know what I'm doing. I don't know why I said it's not an NP sum. You have to do an NP sum. That's how you get the values. Okay. Try that again. There we go. So this is kind of the plot we got. Oh my, what happened? Hopefully you saw that earlier. I just made it empty sum since it's summation. I don't know why I ignore that. So this is what we found in class, and these are our roots right there. So if you zoom in on 0, where it kind of almost gets a discontinuity. So those near those points is where we will get our, or I'm sorry, not near those points, but when the line crosses 0 is when we'll see. So let me make this smaller. I don't know what he did in class. I'm kind of guessing here. Other way around. A little better. So I mentioned earlier, these will change if you change these values, since you'll have more points to play around with. Your discontinuities might get bigger. So if I like drop this up to 500 and maybe I go to like 0.3 and 4, it'll look a little bit different. I think these are higher values now, and spikes are different, but your roots should be the same. I can't even tell at this point, but one of them is 1.26, etc. So you'll see there's points where they cross 0. So there's one at 0.29-ish, one at 1.2. That's the one we're looking for, since this is between the heavy key and the light key. At 2.4, and there's another one further beyond. Or it might not even be here, honestly, since we only have 3. So the fourth one, remember, it's 4 components, so there's 4 roots. The fourth one might be imaginary. So yeah, I'll go put this back so it looks like what we were doing earlier. So yeah, we'll be looking for our root at 1.2, since remember, 2 and 1. Well, I read here, cool, light and key and heavy key. So we choose the ones in between the light key and heavy key, since 1, usually that's where it converges, and that's where also number 2, the more important one, is where that's where the separation between the light key and heavy key will occur with that minimum reflux ratio. So yeah, this is graphing it. I think we're done. Honestly, let's just solve it. So actually solving, maybe up here, and all of this down below was graphing. So let's merge. Bam. Cool. So first thing we do, we'll define our Underwood equation. Did we use Underwood like that? I think so. So theta, that's our only parameter. We're gonna solve the root scalar of this, so it's only one parameter. We have our equation. Do I have it down here? I think it's this, right? So np sum, I think I just copy it, right? Return np sum. Bam. Oh, what am I missing? Parentheses. Okay. Cool. Now we do root scalar of that. We used this before, but it's root scalar since we only have one input or one parameter we're looking for the root of, and we plug in our equation as a parameter. No arguments. Don't really care about the method, so bracket is the one we care about. And remember, this theta we're looking for in between our light key and heavy key. And remember, we always specify, we have to specify that it's a little bigger than the lowest bound and higher, a little bigger than the lowest bound. So 1 plus, and then maybe like 1 e to negative 15. I think in class we did like 1.01, and that worked too. But just to be consistent with what we did before, put a float here, put a decimal. So if you notice, I put decimal sometimes. In lists, you only need to do it once, since you notice there's not a decimal point here to make it a float, but it's good to be consistent. So making a float, adding a decimal point allows the value to be considered a float, which makes it work for certain computations, usually all of them, versus if you didn't have it and you kept it as a integer. So we added to the smallest bound, now we subtract from the largest bound. So hopefully this works. Wow, okay, converge. And yep, like I said, 1.26. So 1.26, somewhere in there. Yeah. I'm actually curious if I evaluate it at 1.26, we should get 0. So just check, why not? Yeah, pretty close to 0. I'm curious to see if I change this also. I mean, I'm going to apply this to the other root, so I'll do one between, what's the other one we had? There's a root somewhere else. We had one between 0.5 and 1, so I'm curious. Out of curiosity, I could actually put 0.5 and 1, I think. Or not. It must be a little bigger and smaller then, so 0.59, or maybe 0.1 and 0.9. That work? There we go. Now we got another root, 0.59. Looks like this is around 0.59-ish. And if I plug that in, I'm just curious. I'm just playing around, checking if things actually work. Completely unnecessary. Yeah, we also get another root. So these roots all work. This isn't me lying to you. These all converge. Well, I did these two, but I'm kind of saving time to not do the other one. But all of these work, but we do choose the one between our heavy key, and our light key. So 1 and 2. And that's what allows our separation with that minimum reflux. So I'll go ahead, delete this, and I'll store this as theta, since that's our actual theta that we found a root for. We found the 0 of that sum equation that we derived earlier. So I'll store that, and this is the root attribute. So root, and then just to check, theta. Yep, 1.26. Cool. Now, go back to our OneNote so we know what we're doing. What else? So now we have theta. What do we do with that? With theta, we go to our vapor, right? Since theta is equal to this phi, they're both equal to, remember, it was our expression here, or here. I don't know why it's hidden right there. Oh, you can't see my cursor. In green, right there. Can barely see it, it's green. Okay, anyway. Get rid of that. So that was that. What's happening? Okay. Yeah. So we'll use our rectifying to get that vapor flow rate corresponding to a minimum reflux ratio. So that V is equal to an NP sum. And remember our XID times D, that's our liquid mole fraction times D. So that's our recovery of our distillate flow rate. Did I specify that? I don't think I did. Oh, we specified recovery right here. So that's actually our recovery, but make sure these are in fractions. We have to multiply the fractions by the actual feed. So it's something like it would be recovery. Oops, what's happening? Recovery times, so the flow rates of our individual components. So let's just multiply these together to get a ZF. So that's our feed flow rates of our components. So I don't know, like Z's times F, just to kind of, what? F total, I'm sorry. Just to keep things more defined here. So this is our feed times the flow rate. So these are the flow rates of each component. Remember, they're all equimolar, and there's only one total feed. That makes sense. So all of these have to be the same feed. So now we have our recovery times those, since we only want to recover a portion of these feeds, and then the rest get stored on the bottom. So notice that the heavier component, heavier than the heavy key, which is already pretty small, is at 0, since we expect none of it to show up. Well, basically none. There'll be some portions, but it'll be basically negligible compared to or relative to the other components. So we multiply our recovery times our feed flow rates. That's what shows up in our distillate. So times ZF. I don't know why there's parentheses. So this is our flow rates of each component at the distillate. And now, yeah, we keep that as an array since, well, it's a sum of all of those. So we don't want to sum this quite yet. So I'll call this, I don't know, D flows, maybe? D flows, since the S for multiple, something like that. So we have that. Now we do our NP sum. So we have our recoveries Yeah. Did I do that correctly? Yeah, rectifying. So those would be flow rates. Distillate times our liquid mole fractions at the distillate. So that D in our equation to my, well, I guess on the screen to my left, that those are flow rates. So, and we already have the recoveries of them. So yeah, we put D flows in there. So D flows times, we have our alphas divided by parentheses, alphas minus, and this will be theta. Let's see what that looks like. What the, I can't spell. This should be like 100 something. Just based on my amazing memorization. Oh yeah, there we go, 108. We're almost there. So now we have our vapor of our rectifying section corresponding to a minimum reflux. After that, our last step here is to plug it right back into our reflux ratio that we derived at the very start. So this good old thing. Yeah. Now these are total flow rates. So notice V is one number. Our distillate has to be one number. So we can't just use our D flows. Now it'll be a sum of the flows. So I'll call it like D total maybe. D total is equal to NP sum. So I know I could just put NP sum in the thing, in the equation, but just to be extremely explicit, so it's pretty obvious what's happening. D total. No, kind of wasting variable names. So it's just summing all of these up. They'll be 50. Yeah, and that's cool since this is in the distillate, and remember our total feed was 100, so we'll actually see the other half, actually a little bit more in the bottoms. So we have, I'll copy down this equation so I can close out that one note. So it's R equals vapor over distillate minus 1. So going back to collab, hopefully you saw all of this. Remember, it's just adding. So now we have a distillate total. Now, at our minimum reflux, we have our vapor we already got, and then our distillate total, which is the sum of all of our distillate flows. So T total. D tot minus 1, please. And I think this was around 1.16. Perfect. We did it. So that's it. Honestly, finishing right on time. So yeah, so this is our minimum reflux ratio. Let me open the problem statement real quick. Back to my screen here. That was not that bad, honestly. What's happening here? That's the wrong thing. No, that's the right thing. Okay. My kickstand makeshift one. Okay, so what we did the Fenske equation, derived. So this was at nearly, it's not infinite, no, I'm sorry. Yeah, this is at a reflux approaching 0. So our operating line was the 45-degree line, and we did our mass balance again with most important parts for honestly Fenske and Underwood was the partition coefficient, which allows us to get the relative constant volatility, our constant relative volatility for both equations, and then we found our expression to find the minimum number of stages given we know all of these values here, which we should since we know what's going in and our desired liquid mole fractions at the condenser and our boiler. Also, you could do this at in between stages, but I mean, usually the whole point is to get total minimum number of stages. So that is at reflux at 0, so no feed, no bottoms, or just lit. Next, we had Underwood, and this was reflux approaching infinity. So we had a slope of our rectifying line, R over R plus 1 approaching 0. And then those pinch points caused by that, as well as our stripping line, which is R plus 1 over R. You have a divide by 0, so it becomes a vertical line. So note that those pinch points are different, like how I drew them in multi-component. The one I drew is binary, but in multi-component, well, honestly, both of these equations shine better in multi-component, but we use binary, relating them to our binary examples we've done before. So this was minimum reflux. At infinite stages, we found that passing streams between stages, honestly, not changing that much. And yeah, that was the whole point there. We used that ratio and our, well, not ratio, but that, I don't know, given factor to evaluate our mass balance, component mass balance relative to the light key at infinite stages using, again, our partition coefficients, a lot of algebraic manipulation, and then finally dividing by kj, our constant relative volatility, or I'm sorry, dividing by, kj, which is our partition coefficient of our heavy key, to relate a vapor flow rate for both our rectifying and stripping sections to a vapor flow rate through, yeah, I don't know what I was trying to say. And then we have this second term here, which I circled, I don't know what color that is, but now in pink. Those terms said by Underwood equal to each other. They share a common root. That's how we find our minimum reflux ratio, the pinch points between the rectifying and stripping that they share. And we subtracted those equations to end up with a final equation that we found the root of in our Python, our collab. So after we found the collab, the root of that, and we also saw it in our graphing function, those roots, we use that theta value, plugged it in back into our rectifying, since that's the one we use. We could also use stripping, but I chose rectifying in this case since that's what our problem statement asked. So in place of phi, we use theta here. They're the same since that's how we got our final equation. So we did it again to find that vapor flow rate corresponding to a minimum reflux ratio. And then with that vapor flow rate, where is it? Right here in green. We found our minimum reflux ratio with our the substitution, with knowing our vapor flow rates and distillate flow rates at a minimum reflux. So that was basically everything we did. Hopefully I summed that up pretty well in a short enough time. But yeah, I believe these are the correct numbers what we got before. So just double checking, 1.16 and 1.26. Okay, cool. I'll leave it, there's 100 there. I don't know, something like this. I'll leave it here so you can see theta and a little bit of the graph. Maybe I'll make it smaller too. Is that good enough? That's so small. Whatever. Anyway. All right. Yeah, that was all. Yeah. Thanks for watching.